Actors Unleashed, Building the Future of Concurrent and Distributed Systems. Chapter 1, The Concurrency Conundrum, Why We Need a New Way. For decades, the march of technological progress in computing was largely predictable. Processors got faster, memory got cheaper, and software could simply ride this wave of increased performance without significant re-engineering. This era, affectionately known as Moore's Law, saw clock speeds of CPUs soar, making single-threaded applications feel snappier with each passing year. However, around the mid-2000s, this comfortable trajectory hit a wall. Physics dictated that packing more transistors onto a chip and cranking up their speed meant exponentially more heat and power consumption. The solution? Instead of making one processor faster, chip manufacturers started putting multiple processors, or cores, on a single chip. This shift ushered in the era of multi-core processors, then multiprocessor systems, and eventually, the ubiquitous distributed systems that power our interconnected world, from cloud applications and streaming services to smartphones and the Internet of Things. But while the hardware evolved dramatically, the way we thought about and built software often lagged. The traditional approach to programming, rooted in sequential execution, suddenly faced a formidable challenge: how to effectively use all those cores and machines without drowning in complexity. This is the concurrency conundrum, and it's why we need a new way. The problem with traditional concurrency: shared memory. Most programming languages and operating systems were designed with a foundational assumption. Code runs one instruction after another in a predictable sequence. When developers needed to perform multiple tasks seemingly simultaneously, they turned to threads. A thread is an independent sequence of execution within a program. Imagine multiple cooks, threads in a single kitchen, a program's memory space, all sharing the same pantry data and workbench, CPU. This shared kitchen or shared memory is where the trouble begins. The shared memory challenge. When multiple threads can simultaneously read from and write to the same memory locations, chaos can ensue. It's like two cooks simultaneously grabbing ingredients from the same jar, or worse, trying to put different ingredients into the same bowl at the same time. Race conditions. One of the most insidious problems is the race condition. This occurs when the outcome of a program depends on the unpredictable timing or sequence of thread execution. Analogy: consider an online shopping cart. You have one cook, thread A, trying to add an item, and another cook, thread B, trying to remove an item simultaneously. Both read the current count, e.g., 5 items. Thread A adds 1, making it 6, but before it can write the new total, thread B removes 1, thinks it's 4, and writes 4. The correct answer should have been 5, but due to the race, you end up with 4 or 6, depending on who wrote last. These bugs are notoriously difficult to find because they might only appear under specific, hard-to-reproduce timing conditions. Deadlocks. If race conditions are about unpredictable outcomes, deadlocks are about complete gridlock. A deadlock occurs when two or more threads are stuck, each waiting for the other to release a resource that it needs to proceed. Analogy: imagine two cars approaching a four-way intersection. Both need to pass through, but if each car waits for the other to move before it proceeds, both remain stuck indefinitely. In computing, thread A holds resource X and needs resource Y, while thread B holds resource Y and needs resource X. Neither can move forward, and the entire program grinds to a halt. Livelocks. Less common but equally problematic are livelocks. Here, threads aren't truly blocked, but they are constantly changing their state in response to each other in a way that prevents them from making actual progress. Think of two polite people trying to pass each other in a narrow corridor. They both move aside, then both move back, repeatedly, never getting past. Complexity of locks and critical sections. To manage these issues, programmers developed synchronization primitives: locks, mutexes, semaphores, and monitors. These mechanisms allow threads to temporarily block or reserve access to shared data, creating critical sections of code where only one thread can execute at a time. Difficulty: while necessary, these primitives are notoriously difficult to use correctly. Forgetting to acquire a lock, acquiring the wrong lock, or releasing a lock too early can lead to subtle, catastrophic bugs. Performance overhead. Locks introduce overhead. Threads waiting for a lock consume CPU cycles or involve costly context switches. Composability. Perhaps most importantly, locks don't compose well. Building a secure, thread-safe library is hard enough. Trying to combine multiple independent thread-safe components often reintroduces concurrency issues and deadlocks. Reasoning about the behavior of a system with many intertwined locks becomes a Herculean task. The debugging nightmare. The nature of concurrency bugs, their non-deterministic, timing-dependent behavior, makes them a debugger's worst enemy. They might appear only rarely, under specific load conditions, and often disappear when you try to attach a debugger, a phenomenon known as the Heisenbug, after Heisenberg's uncertainty principle. The growing need for scalability and resilience. Beyond just managing multiple cores on a single machine, modern applications increasingly rely on distributed systems, networks of computers working together. Think of Netflix streaming video to millions, Amazon fulfilling countless orders, or any cloud service. In such environments, traditional shared memory concurrency techniques become utterly impractical. You can't put a lock on data that resides on a different server across a network. Furthermore, users expect systems to be always on. Telecommunication networks, financial trading platforms, and critical web services cannot afford downtime. Traditional applications that crash due to a single thread error are unacceptable. We need systems that are not just fast, but also scalable, can handle more users and data by adding more resources, and resilient, can gracefully handle failures without collapsing. The concurrency conundrum, therefore, isn't just an academic problem. It's a fundamental challenge for how we build the software that underpins our modern world. It demands a paradigm shift, a different way of thinking about interaction and state. This is where the actor model emerges as a powerful and elegant solution. Chapter 2, Enter the Actor, a new paradigm for concurrency. In the face of the concurrency conundrum, computer science has explored various avenues. While threads and locks seemed like an intuitive extension of sequential programming, their inherent complexity for parallel systems ultimately revealed a fundamental flaw in modeling concurrent interaction. What if, instead of sharing memory and locking it, we modeled computation as completely isolated, communicating entities? This radical idea laid the groundwork for the actor model, a concept that has quietly been shaping the architecture of the most robust and scalable systems for decades. Carl Hewitt and the Birth of the Actor Model, 1973. The actor model was first introduced in 1973 by Carl Hewitt, Peter Bishop, and Richard Steiger at the Massachusetts Institute of Technology, MIT. This was a vibrant era of computing research, driven by ambitious goals in artificial intelligence, AI, and the burgeoning need for effective parallel computation. Hewitt and his colleagues weren't just looking for a new programming construct. They were seeking a mathematically sound and principled foundation for concurrent computation. They envisioned a world where systems could seamlessly scale, recover from failures, and process multiple tasks in parallel without the pitfalls of shared memory. Hewitt's work aimed to move beyond the von Neumann model of computation, which describes a single process manipulating memory, to a more distributed and communicative model directly applicable to parallel machines. His intuition was profound. If you want independent things to work together, they should communicate like independent entities, not by wrestling over shared resources. What is an actor? The fundamental building block. At its heart, the actor model is beautifully simple. It defines a system as being composed entirely of actors. Think of an actor as a tiny, isolated, self-contained digital person or a microservice in miniature. Each actor is fundamentally independent, possessing its own private state, its own behavior, and a unique address. Consider these core capabilities of any actor. Receive messages. An actor waits for and processes messages sent to it. Make local decisions. Based on the message it receives and its internal state, it decides what to do. Create new actors. It can spawn new workers or helpers to delegate tasks. Send messages. Its primary way of interacting with the outside world, other actors, or even itself. Designate next behavior. It can change how it will respond to subsequent messages. The core principles of the actor model. These capabilities are governed by a few critical principles that differentiate actors from traditional objects or threads. Encapsulation, isolation. This is the bedrock principle. Each actor has its own private, isolated memory, known as its state. This state is entirely local to the actor and inaccessible to any other actor directly. Other actors cannot look at, modify, or even peek into an actor's internal state. Analogy: imagine an actor as a person dwelling in their own private room. Anything inside that room, their thoughts, belongings, is theirs alone. No one else can simply walk in and rearrange their furniture or read their diary. This fundamental isolation is what prevents race conditions and ensures that an actor's internal logic is always consistent with its own perspective. Asynchronous message passing. The only way actors communicate with one another is by sending messages. Non-blocking send. When an actor sends a message, it doesn't wait for the recipient to process it. It fires and forgets, immediately continuing with its own tasks. This is crucial for keeping systems responsive and preventing deadlocks. Mailbox. Every actor has an incoming queue, often called a mailbox. When a message is sent to an actor, it gets placed in that actor's mailbox. The actor then processes messages from its mailbox, one at a time, on its own schedule. Analogy: it's like sending a letter through the postal service. You drop it in a mailbox, and you don't wait for it to be delivered and read before you go about your day. The recipient processes their mail when they choose to. No shared mutable state. This is the golden rule, directly flowing from encapsulation and message passing. Because actors communicate only through messages, and each actor's state is private, there is no shared mutable state between actors. This elegantly sidesteps the entire class of problems, race conditions, deadlocks, livelocks, that plague traditional shared memory concurrency models. If there's nothing to fight over, there's no fight. Sequential processing of messages. While an actor system as a whole is highly concurrent, many actors processing messages in parallel, each individual actor processes messages one at a time, sequentially, from its own mailbox. This internal sequentiality is vital. It means the actor doesn't need internal locks or synchronization primitives for its own state. It guarantees that an actor's internal state updates are always consistent and predictable. How an actor works: high-level flow. An actor is born, created, typically by another actor. It settles into a waiting state, listening for messages. When a message arrives sent by another actor, it's placed in the actor's mailbox. The actor picks the next message from its mailbox, usually first in, first out. It processes the message using its current behavior and its internal state. During this processing, it can modify its own private state, create new actors to delegate subtasks, send messages to other actors, including itself. Crucially, define how it will respond to the next message it receives, its next behavior. Once processed, it goes back to waiting for the next message in its mailbox. Why this approach simplifies concurrency? By adhering to these principles, the actor model simplifies the complexities of concurrent programming dramatically. It shifts the burden from managing shared state and synchronization to designing clear messages and independent, self-contained computational units. Thinking in terms of actors that communicate solely by messages feels more natural for many large-scale, distributed problems, leading to systems that are not only easier to reason about, but also inherently more scalable and resilient. It offers an elegant solution to the very problems that entangled traditional concurrency models. Chapter 3: Anatomy of an Actor, Inside the Digital Brains. In the previous chapter, we introduced the actor model as a new paradigm for concurrency, highlighting its core principles of isolation and message passing. Now, let's peel back the layers and examine the fundamental components that make up an individual actor. Understanding these parts is crucial to grasping how actors operate and why they are so powerful in building robust systems. Every actor, no matter how simple or complex its task, is essentially composed of three main parts: an identity, a state, and a behavior, all managed through its mailbox. Identity, address. Just like every person has a name and address, every actor has a unique identity or address. This address is its unique identifier within the actor system, allowing other actors to find it and send messages to it. It's not just a label, it's the precise postal code for an actor's mailbox. Analogy: think of an actor's identity as its unique telephone number or email address. When you want to communicate with a friend, you dial their number or send an email to their address. You don't need to know where they physically are, whether they're at home, at work, or traveling abroad. You just need their address. Location transparency. This concept of location transparency is fundamental. A sending actor doesn't need to know if the recipient actor is on the same processor core, a different machine in the same data center, or even across the globe. The actor system's underlying infrastructure handles the routing of the message to the correct recipient, regardless of its physical location. This simplifies development, as you can design your system without being constrained by deployment topology. State. The state of an actor is its private, internal memory. This is where an actor stores all the data it needs to perform its tasks, variables, counters, lists, or any other information that defines its current condition or memory. The crucial rule. As briefly mentioned before, an actor's state is entirely private and inaccessible to any other actor directly. This is perhaps the most significant departure from traditional object-oriented programming, where objects often expose their internal data or allow direct modification. For an actor, its state is sacred. Analogy: an actor's state is like a person's private thoughts, memories, and personal belongings. These are unique to that individual and cannot be directly accessed or altered by anyone else. If someone wants to know something about you or influence you, they have to ask or tell you something, and you decide what to reveal or how to react. Implication for consistency. This strict encapsulation means that only the actor itself can modify its own state. Because an actor processes messages one at a time, there's no possibility of two different threads simultaneously trying to update the same piece of data within that actor. This eliminates internal race conditions and greatly simplifies reasoning about the actor's consistency. While other actors can send messages that influence an actor's state, the actor always remains in control of its own internal data. Behavior. The behavior of an actor defines how it reacts to the messages it receives. It's the set of rules, the logic, or the function that the actor executes when a message arrives in its mailbox. Message interpretation. An actor's behavior determines how it interprets a message, what actions it takes based on that message and its current state, and what new messages it might send out to other actors. Dynamic change, the become primitive. One of the most powerful features of an actor is its ability to change its behavior dynamically for future messages. This is unlike a typical object, which maintains a fixed set of methods. An actor can effectively transform itself into a different kind of entity with a completely new set of reactions after processing a message. Analogy: imagine a superhero. Our hero might start in an idle behavior, just waiting. When a call for help message comes, they might become a responding to crisis behavior, which now dictates how they react to villain attack messages or civilian in danger messages. After saving the day, they might become relaxing behavior, which reacts to a take nap message differently than a villain attack message. The core identity remains, but how they function changes completely. Practical example. Consider an actor handling a network connection. Initially, its behavior might be connecting, only accepting messages like connection established or connection failed. Once a connection established message is processed, the actor might become connected, now accepting messages like send data or receive data. If it then receives a disconnect message, it could become disconnected, no longer accepting data messages. This dynamic behavior capability allows actors to elegantly model finite state machines and sequential processes without complex external logic or flags. Mailbox. Every actor has a mailbox, which is essentially a queue where incoming messages are stored. When another actor sends a message, it doesn't directly call a method on the recipient actor. Instead, it places the message into the recipient's mailbox. Decoupling communication. The mailbox acts as a buffer, decoupling the sender from the receiver. The sender doesn't need to wait for the receiver to be ready. It just drops the message in the box and moves on. Sequential processing guarantee. This is critical. An actor processes messages from its mailbox one at a time, in sequence. Typically, messages are processed in a first-in, first-out, FIFO order. This sequential processing is the ultimate guardian of the actor's internal state consistency. Since the actor handles only one message at a time, it inherently avoids internal race conditions where multiple operations might try to modify its state concurrently. Analogy: the mailbox is much like a physical letterbox. Anyone can drop letters into it at any time. The owner of the letterbox, the actor, picks up letters from it one by one, reads them, and then responds accordingly. While they are reading one letter, they aren't simultaneously reading another. They deal with them sequentially. Message processing cycle. To tie it all together, here's a simplified look at an actor's life cycle. An actor is created and starts listening for messages. When a message arrives, sent by another actor, it's placed into the actor's mailbox. The actor system notifies the actor, or the actor continuously checks its mailbox. The actor picks the next message from its mailbox. It applies its current behavior to process the message, potentially updating its internal state, sending new messages to other actors, creating new actors, or changing its future behavior. Once the message is fully processed, the actor becomes ready to pick up the next message from its mailbox. This simple yet profound cycle, built upon the pillars of identity, state, and dynamic behavior, orchestrated asynchronously via mailbox, forms the powerful foundation of the actor model. It's this well-defined internal structure and strict communication protocol that allows actors to collectively build highly concurrent, scalable, and resilient systems. Chapter 4: Messages and Behaviors. The Dance of Interaction. In the previous chapter, we dissected the actor, looking at its identity, state, and behavior, all connected by its mailbox. Now, we turn our attention to how these individual digital entities interact with each other. Communication is the lifeblood of any actor system, and in this world, communication takes a very specific, disciplined form: message passing. It's the dance of interaction that brings the individual actors to life, allowing them to collaborate and perform complex tasks. The message, the atom of interaction. If actors are the fundamental building blocks of computation, then messages are the fundamental particles of interaction. What exactly is a message in the actor model? A message is a piece of immutable data that an actor sends to another actor. Because it's immutable, meaning it cannot be changed after it's been created and sent, there's no risk of a message being altered by one actor while another is still processing it, or while it's in transit. This is a critical design choice that prevents a whole class of subtle bugs involving shared data. Analogy: think of a message as a sealed letter or a dedicated courier package. Once you've written the letter, sealed the envelope, and sent it, you cannot go back and change its contents. The recipient will receive exactly what you put in the envelope. The message also carries clear intent. It's not just random data. It's a command, add customer, a query, get balance, or an event, order placed, sending messages. Communication in an actor system is predominantly asynchronous. This means that when an actor sends a message, it doesn't wait for the recipient actor to process it. It simply fires and forgets. It puts the message into the recipient's mailbox and then immediately continues with its own work. The fire and forget model. This non-blocking nature is a cornerstone of actor systems' responsiveness and scalability. The sending actor doesn't pause its own execution, allowing it to remain busy and responsive. Analogy: it's like sending a text message. You type it, hit send, and immediately go back to whatever you were doing. You don't stand there waiting for the recipient to respond or even to read it. The message is dispatched, and your part is done. No explicit return values. Because message passing is asynchronous, there isn't a direct return value in the traditional sense of a function call. If an actor needs a response to a message it sent, the recipient actor must explicitly send another message back to the original sender. The original sender can then process this reply message when it arrives in its own mailbox. The sender concept. To facilitate replies, actor systems typically provide a way for the recipient actor to know who sent the message. This often comes in the form of a sender reference or a reply to address included with the message when it's put into the mailbox. Analogy: if you receive a letter, the return address tells you who sent it. You can then write a new letter and send it back to that address. Reliability of delivery, briefly. In perfect conditions, messages always arrive, and they always arrive in the order sent. However, in distributed systems, especially over networks, things can go wrong. Most actor frameworks default to providing, at most once, delivery guarantees between non-local actors. This means a message will arrive 0 times or once, but never more than once. Messages can be lost. For situations requiring higher guarantees, at least once or exactly once, specialized mechanisms built on top of the basic message passing are required, often involving acknowledgements or persistence layers. This highlights that distributed programming is inherently complex, and actors simplify it, but don't magically make the network perfect. Receiving and processing messages. When a message arrives at an actor's mailbox, it waits its turn. As we discussed, each actor processes messages sequentially from its mailbox, ensuring its internal state remains consistent. The actor's event loop. Conceptually, every actor runs a single-threaded event loop. This loop continuously polls its mailbox, takes the next message, processes it according to its current behavior, and then goes back to the mailbox for the next message. This disciplined approach means an actor can never be caught off guard by concurrent operations on its state. Pattern matching for messages. Actors typically use concepts like pattern matching, or simply if-else statements depending on the language, to inspect the incoming message and decide what logic to execute. The actor checks the type and content of the message and dispatches it to the appropriate handling code within its behavior. Conceptual example. If this is a deposit message, then add the amount to my balance. If it's a withdraw message, then check balance, subtract amount. If it's a print statement message, then format and send details to sender. Tell versus ask, conceptual. While the fundamental way to send a message is called tell, the fire and forget method, many frameworks offer a convenience method often called ask. Tell, this is the pure asynchronous send. Actor, message, common notation. You send a message, and you don't stand there waiting for a reply. Ask, this method provides a way to get a future or promise back, which will eventually contain the reply message from the recipient. It feels more like a traditional synchronous call, but internally, it's still a fire and forget message send, with a temporary internal actor created to await and capture the reply message. It's a useful pattern for request-response interactions in an otherwise asynchronous world. Changing behavior, they become primitive. One of the most elegant and powerful aspects of the actor model is an actor's ability to dynamically change its behavior. An actor isn't just a static collection of methods. It's a living entity that can adapt how it responds to future messages. Concept. After processing a message, an actor can designate a new behavior that will be used for all subsequent messages arriving in its mailbox. This means the exact same message, sent to the same actor, might be handled completely differently depending on the actor's current behavior. Analogy, imagine a traffic light. It starts in a red state behavior. When it receives a timer tick message indicating it's time to change, its red state behavior tells it, "Okay, I processed the tick. For the next message, I will now be in green state behavior." When the next timer tick comes, green state behavior takes over, then yellow state, and so on. The traffic light itself remains the same actor, but its internal logic evolves. Practical examples. Account state. An account actor could start in an unlocked behavior, which fully processes withdraw messages. If it receives a lock account message, its unlocked behavior might process this by changing itself to a locked behavior. Now, if a withdraw message arrives, the locked behavior might simply reject it or notify the sender that the account is locked. A subsequent unlock account message would transition it back to unlocked. File downloading. An actor tasked with downloading a large file could start in a waiting for first chunk behavior. Once the first data chunk message arrives, it becomes a downloading in progress behavior, which handles subsequent chunk data messages, assembling the file. When a download complete message arrives, it becomes a file-ready behavior, possibly notifying another actor and no longer accepting chunk data. This ability to change behavior is a sophisticated form of what's known as a finite state machine, but it's built directly into the actor's design. It allows complex, sequential workflows and dynamic policies to be modeled simply and robustly inside single, isolated actors, without the need for external state transition logic. It's what truly breathes life into the digital brains we discussed in the previous chapter, enabling them to react, adapt, and evolve in the dynamic world of concurrent computation. Chapter 5. Building Robust Systems, Supervision and Fault Tolerance. In the world of traditional software development, the mantra has long been prevent all errors. We build highly defensive code, throwing exceptions, validating every input, and trying to anticipate every possible problem. The goal is to build a fortress of logic that is impervious to failure. Yet, anyone who has worked on complex systems knows the truth. Failures are inevitable. Bugs creep in, networks falter, hardware degrades, and unexpected user inputs wreak havoc. So, what if, instead of fighting against this inevitability, we embraced it? This radical idea lies at the heart of the actor model's approach to reliability, the let it crash philosophy. The let it crash philosophy. The let it crash philosophy, famously championed by the creators of Erlang, the programming language that fully embodies the actor model, is counterintuitive at first glance. It posits that it's more effective to detect failures immediately, clean up the corrupted state, restart the failing component in a known good state, allow the rest of the system to continue operating. Instead of trying to prevent every conceivable error within a component, you design that component to be small, isolated, and, if it fails, to crash quickly and spectacularly. The responsibility for handling that crash is then delegated to a supervising entity. Analogy: imagine a complex machine on an assembly line. Traditional thinking says, let's make sure every part of this machine is absolutely perfect so it never, ever breaks. The let it crash philosophy says, it's okay if a small part of this machine breaks. We have a robust system to detect the break, automatically swap in a new, working part, and keep the assembly line moving with minimal interruption. This approach emphasizes recovery over prevention at the lowest level, leading to overall system resilience. This approach is particularly powerful because it acknowledges the difficulty of writing perfect code, especially in concurrent and distributed environments. By isolating components' actors and providing robust recovery mechanisms, the system can self-heal, achieving uptime and reliability levels that are incredibly difficult to reach with traditional methods. Supervision hierarchies, the family tree of actors. How does a system know when a component crashes and how to recover it? This is where supervision hierarchies come into play. In an actor system, actors are typically organized into a tree-like structure, where a parent actor creates and supervises child actors. The parent's role. A parent actor's primary responsibility is to create its children, oversee their operations, and react if any of its children fail. It's like a manager overseeing a team. The manager delegates tasks to team members, children. But if a team member encounters a serious problem, the manager steps in to resolve it. Crucially, the parent only gets involved if a child crashes or experiences a significant, unhandled error. Healthy, well-behaved children don't bother their parent. Relationship, not just communication. This parent-child relationship is different from simply sending messages between actors. It's a structural relationship that defines responsibility for fault detection and recovery. If a child actor encounters an error it cannot handle itself, it throws a signal like an exception to its parent. Supervision strategies. When a parent actor receives a failure notification from one of its children, it applies a predefined supervision strategy. These strategies dictate what action the parent should take. Resume. The parent tells the child actor to continue processing as if nothing happened. When to use. This is suitable for minor, transient issues where the child's internal state is not corrupted, and retrying the operation will likely succeed, e.g., a simple network glitch. The child just picks up the next message in its mailbox. Restart. The parent stops the errant child actor, effectively destroying its internal state, creates a new instance of that child actor, from scratch, in its initial clean state, and then restarts its message processing. When to use. This is the most common and powerful strategy. It's ideal when a child actor's internal state might have become corrupted due to the error. By restarting, the actor gets a clean slate. Any messages that were in the mailbox at the time of the crash are usually lost, unless explicitly persisted elsewhere, and the new instance starts anew. This is fundamental to let it crash. Don't try to fix the internal broken state, simply discard it and get a fresh, working component. Stop. The parent terminates the child actor permanently. When to use. This is used for fatal, unrecoverable errors, where the child actor can no longer fulfill its purpose, or its failure indicates a larger, unfixable problem. For example, if a database connection actor fails because the database no longer exists, there's no point in restarting it. Escalate, the parent acknowledges the failure but doesn't handle it directly. Instead, it passes the failure notification up to its own parent, its supervisor. When to use. This happens when the parent actor doesn't have a suitable strategy for the type of failure, or if the failure implies a problem with the parent's own assumptions or environment. This can lead to a cascade of escalation up the hierarchy until a supervisor is found that can handle the failure, or until it reaches the system's top-level guardian. 1-for-1 versus all-for-one. Some frameworks offer variations. With a 1-for-1 strategy, only the failing child is affected. With all-for-one, if one child fails, all its siblings are also stopped or restarted, based on the assumption that a failure in one might indicate a shared problem affecting the entire group managed by that parent. The death watch mechanism. Beyond supervision, actors can also watch other actors for termination. If an actor is watching another and the watched actor stops, either gracefully or due to a crash and stop strategy, the watcher actor receives a special terminated message. Use cases. This is useful for actors that depend on external resources or other critical services. For instance, an actor managing a user session might watch an actor handling the database connection. If the database connection actor terminates, the session actor can then gracefully close the user session or attempt to re-establish the connection. It's a way to react to the lifecycle events of independent actors. Resilience patterns in actor systems. The supervision model forms the backbone of fault tolerance, but it's complemented by broader design patterns that enhance overall system resilience. Bulkheading. This pattern involves isolating parts of the system so that a failure in one section does not propagate and bring down the entire system. In actor systems, this is naturally achieved by structuring supervision hierarchies. Critical subsystems can be managed by dedicated supervisors that apply very strict recovery rules, insulating them from failures in less critical, more volatile parts of the application. If one bulkhead fills with water, the others remain safe. Circuit breaker. Imagine an electrical circuit breaker that trips when there's an overload, protecting the rest of the circuit. In software, a circuit breaker pattern protects an application from continuously trying to access a failing external service, like a slow database or an unresponsive API. If a certain number of calls to that service fail within a time period, the circuit breaker opens, meaning all subsequent calls to that service are immediately rejected for a defined period. After some time, it half opens to allow a few test calls through, and if they succeed, it closes again, allowing normal traffic to resume. This gives the failing service time to recover and prevents the application from wasting resources on doomed requests. Timeouts and retries. While sending messages is asynchronous, an actor might eventually need a response from another actor or an external system. Setting timeouts on these interactions is crucial. If a response isn't received within a specified period, the original actor can assume a failure and react accordingly, e.g., log an error, send a failure message to its client, or initiate a retries. Retries, often with exponential backoff, waiting longer between retries, can help overcome transient issues without overwhelming a struggling service. Why this approach is powerful. By combining isolated actors, robust supervision hierarchies, and proven resilience patterns, the actor model facilitates the creation of systems that are self-healing. They can detect and recover from many types of failures automatically, without human intervention. Highly available. Their ability to recover quickly from component failures minimizes downtime and keeps the system operational. Easier to reason about. Instead of complex, interwoven exception handling throughout your codebase, The error handling logic is centralized at the supervisor level, making individual actors simpler and easier to understand. Battle-tested, this approach is not theoretical. It has powered critical infrastructure like telecommunications switches and massively scaled web services for decades, demonstrating its effectiveness in the most demanding environments. While the "let it crash" philosophy might seem counterintuitive at first compared to traditional defensive programming, it's a powerful acknowledgement of reality. Failures happen. The actor model provides the tools and the mindset to design systems that don't just survive these failures but emerge stronger and more reliable. Chapter 6: Actors in Action. Real-world frameworks. So far, we've explored the foundational concepts of the actor model. Its origins, its core principles of isolation and message passing, and its revolutionary approach to building fault-tolerant systems through supervision. These are abstract, powerful ideas, but how do they translate into concrete software that powers our modern world? The answer lies in the various frameworks and languages that have adopted and implemented the actor model. While the principles remain universal, each framework brings its own flavor, strengths, and ecosystem. In this chapter, we'll delve into the most prominent and influential implementations of the actor model, showing how these abstract concepts are put into action. Erlang/OTP, the pioneer and progenitor. If you want to understand the actor model, you must understand Erlang. Developed at Ericsson in the mid-1980s, Erlang was initially conceived as a proprietary language for building robust, fault-tolerant, and highly concurrent telecommunication systems. The engineers at Ericsson faced a monumental challenge: creating telephone switches that could handle millions of concurrent calls, operate continuously for years without downtime, and even be updated with new software while running. Their solution implicitly became one of the most successful practical applications of the actor model. Language and philosophy. Erlang and its accompanying framework OTP, Open Telecom Platform, wasn't just a language. It was a complete philosophy for building carrier-grade software. Erlang's virtual machine, Beam, supports millions of lightweight processes, which are essentially actors, each with its own isolated memory, communicating asynchronously. OTP as a platform. OTP provides a rich set of libraries and design principles that abstract common concurrency patterns. For instance, OTP offers standard behaviors like GenServer for generic client-server interactions, GenEvent for event handling, and, crucially, supervisor behaviors that directly implement the supervision hierarchies we discussed. Hot code swapping. A unique feature of Erlang/OTP is its ability to perform hot code swapping. This means you can update a running system by replacing parts of its code without taking it offline. This was essential for telephone switches that couldn't afford a single moment of downtime. Real-world impact. Erlang's influence extends far beyond telecoms. One of the most famous success stories is WhatsApp. Before its acquisition by Facebook, WhatsApp managed over 900 million users with a remarkably small engineering team. This was largely attributed to Erlang's ability to handle massive concurrency and maintain high availability with incredible efficiency. It's often quoted that half of all mobile phone calls route through Erlang. Beyond WhatsApp, Erlang powers critical components in financial systems, instant messaging platforms, and countless IoT solutions. Joe Armstrong, one of Erlang's creators, famously quipped that, "If I have seen further than others, it is by standing upon the shoulders of giants. And mostly because I work on a system that refuses to crash." Akka, the JVM powerhouse. While Erlang was building its legacy, the actor model remained a niche concept for many years. That began to change significantly with Akka. Akka is a toolkit for building concurrent, distributed, and resilient message-driven applications on the JVM, Java Virtual Machine. It brings the power and principles of the actor model to the vast ecosystem of Java and Scala developers. Origin. Developed by TypeSafe, now Lightbend, Akka rose to prominence by addressing the concurrency challenges faced by developers working with traditional JVM threads and locks. It provided a scalable, fault-tolerant alternative that fit within existing enterprise environments. Features. Akka Actors. The core Akka module provides a robust, high-performance implementation of the actor model, including supervision, mailboxes, and dynamic behavior changes. Akka cluster allows actors to be distributed across multiple JVMs, forming a single, logical actor system that can scale out horizontally. This module handles membership, leader election, and remote communication seamlessly. Akka persistence enables actors to store their state durably, allowing them to recover their exact state even after a crash or restart. This often involves event sourcing and snapshots. Akka streams HTTP. Beyond actors, Akka provides powerful tools for reactive stream processing and building highly performant HTTP services, deeply integrated with its actor capabilities. Why popular? Akka's strength lies in bringing the actor model's benefits to a massive existing developer base. Developers can leverage their Java or Scala skills while adopting a paradigm designed for modern, distributed computing. Its comprehensive documentation, active community, and battle-tested nature have made it a go-to choice for building microservices, real-time data pipelines, and event-driven architectures. Microsoft Orleans. Virtual actors for cloud native. Emerging from Microsoft research, Microsoft Orleans takes a slightly different approach to the actor model, often referring to its actors as grains and introducing the concept of virtual actors. Orleans aims to simplify the development of highly scalable, distributed applications, especially in cloud environments, by taking on much of the infrastructure complexity itself. Origin, initially developed for internal use at Microsoft, powering services for the popular Xbox game Halo, Orleans was later open-sourced and became a key technology for cloud-native applications built on the .NET platform. Concept of virtual actors. Grains. In Orleans, grains are virtual because developers don't explicitly manage their lifecycle: creation, activation, deactivation. You simply send a message to a grain's ID, and the Orleans runtime transparently activates or reactivates the grain on a suitable server, routes the message, and manages its state. When a grain is idle for some time, the runtime automatically deactivates it, freeing up resources. This gives the illusion that all actors are always on and ready to receive messages without requiring them to consume resources constantly. Features: Orleans provides built-in clustering, automatic state persistence to various storage backends, reminders for scheduled tasks, and stream support. It excels at maintaining location transparency and managing distributed state without explicit developer intervention. Advantages: Orleans significantly reduces the boilerplate code and complexity traditionally associated with distributed systems. Developers can focus almost entirely on the business logic of their grains, letting the Orleans runtime handle the intricacies of concurrency, distribution, and fault tolerance. Use cases: Orleans is particularly well-suited for interactive cloud services, gaming backends, like its original application for Halo IoT device management, where many small, independent stateful entities need to be managed, and any application requiring a large number of independent, distributed, and persistent entities. Other actor initiatives. The influence of the actor model is not limited to these three giants. Elixir. Built on the Erlang virtual machine Beam, Elixir is a modern, dynamic, functional programming language that offers a more approachable syntax than Erlang while leveraging all of Erlang/Ops battle-tested runtime capabilities for concurrency and fault tolerance. It's becoming increasingly popular for web development, Phoenix framework, and high concurrency systems. Go goroutines and channels. While not a strict implementation of the actor model, Go's concurrency primitives, goroutines, lightweight threads managed by the Go runtime, and channels for communicating between goroutines, allow developers to build systems that behave in an actor-like manner. Goroutines can be designed to encapsulate state, and channels can be used for exclusive message passing, mimicking actor principles. Pony, a relatively newer language that explicitly implements the actor model, focusing on safety without locks, using a unique type system. Conclusion: from Erlang's telecom roots to Akka's presence in the JVM ecosystem and Orleans' cloud-native simplicity, these frameworks demonstrate the versatility and power of the actor model. They provide concrete, production-ready tools for building systems that are inherently designed to be concurrent, scalable, and resilient. While they offer different developer experiences and cater to different platforms, they all stand on the shoulders of the fundamental principles laid out by Carl Hewitt: isolation, message passing, and supervisor-based fault tolerance. Understanding these frameworks is key to applying the actor model in the real world. Chapter 7: Scaling Out. Distributed actors. Our journey through the actor model, so far, has largely focused on how actors bring order to concurrency within a single application or machine. We've seen how they handle multiple tasks simultaneously, manage states safely, and recover from individual failures. But the real power of the actor model, the feature that makes it uniquely suited for modern computing, is its ability to extend seamlessly from concurrency to distribution. In today's world, a single computer, no matter how powerful, is rarely enough to handle the demands of global services like social media, e-commerce, or real-time analytics. These systems require scaling out across many machines, each potentially in different geographical locations. This distributed environment, however, presents a whole new set of formidable challenges. The challenge of distribution. When you move computation from a single machine to a network of machines, you introduce complexities that are absent in a local setting. Network latency. Messages between actors on different machines have to travel over a network. This introduces delays that are orders of magnitude greater than communication within a single machine. While local message passing might take nanoseconds, network communication can take milliseconds or even hundreds of milliseconds across continents. Network unreliability. Networks are inherently unreliable. Messages can be lost, duplicated, arrive out of order, or simply be delayed indefinitely. There's no guarantee that a message sent will ever reach its destination. Partial failure. In a distributed system, a part of the system can fail while others continue to operate. One server might crash, a network cable might be cut, or a hard drive might fail, yet the rest of the system carries on, often unaware of the specific failure. This contrasts with a single machine where a critical failure often brings down the entire application. These fallacies of distributed computing, like the network is reliable or latency is zero, are often overlooked in system design, leading to brittle and unpredictable applications. The actor model, due to its fundamental principles, is uniquely positioned to handle these realities. Embracing location transparency. One of the most elegant aspects of a well-designed distributed actor system is location transparency. This is the ideal where an application developer doesn't need to know, or ideally, care, whether an actor being messaged is running on the same process, the same machine, or a different machine across a network. The illusion. The actor system's runtime creates the illusion that all actors exist in a single, unified address space. You send a message to an actor's address, just as you would for a local actor, and the system handles the complexities of routing that message to its current physical location. How it works. This is achieved through sophisticated underlying mechanisms. When a message is sent to a remote actor, the system serializes the message, converts its data into a format that can be transmitted over a network, sends it to the destination machine, deserializes it back into its original form, and then places it in the remote actor's mailbox. All this happens seamlessly, abstracted away from the application code. Benefit: location transparency greatly simplifies development of distributed applications. Developers can focus on the logical interactions between actors without being burdened by boilerplate code for network communication, serialization, or remote endpoint management. Clustering actor systems. To achieve location transparency and manage actors across multiple machines, actor frameworks employ clustering. A cluster is a group of interconnected machines, nodes, that cooperate to form a single, logical actor system. Membership management. Nodes in a cluster need to know about each other. They use various techniques, often based on gossip protocols, to periodically exchange information about their presence, health, and changes in the cluster membership. This allows nodes to discover new members or detect when existing members have left or crashed. Leader election, if applicable. In some cluster configurations, A leader node might be elected to manage certain shared responsibilities, such as coordinating state, managing singleton actors, actors guaranteed to have only one instance running in the entire cluster, or orchestrating system-wide operations. This election process is automatic and highly fault-tolerant. Split brain problem. A critical challenge in clustering is the split brain problem. This occurs when network partitions divide a cluster into two or more isolated segments, each believing it's the sole, authoritative cluster. This can lead to inconsistencies and data corruption. Robust actor frameworks employ strategies, like needing a majority of nodes to form a cluster, or fencing mechanisms to forcibly remove problematic nodes to detect and resolve split-brain scenarios, ensuring data integrity. State management in distributed actors. While an individual actor's state is encapsulated and private, building large-scale distributed systems often requires managing state that survives machine restarts or network failures. Persistence. For critical actors whose state must survive crashes or planned shutdowns, frameworks provide mechanisms to persist an actor's state to disk or a database. This means before an actor shuts down or crashes, its current state can be saved, e.g., to a NoSQL database, a relational database, or a dedicated log. When the actor is later restarted or recovered on a different machine, it can reload its saved state and resume processing from where it left off, maintaining continuity. Event sourcing. A powerful pattern often used with actor persistence is event sourcing. Instead of just saving the current state, an actor saves every event or message that causes a state change. To reconstruct an actor's state, the system simply replays all these historical events in order. This provides an audit trail and allows for advanced capabilities like deriving different views of the data or debugging by replaying specific scenarios. Replication sharding. For extremely high availability or scalability, an actor's state might be replicated across multiple nodes. Alternatively, large datasets can be sharded, partitioned, across many actors, with each actor responsible for a specific subset of data. This allows for parallel processing and distribution of workload. Scalability patterns building on actors. The inherent design of actors lends itself naturally to patterns that allow systems to scale to immense proportions. Work distribution/load balancing. For tasks that can be performed by multiple, identical workers, e.g., image processing, data transformation, a router actor can distribute messages to a pool of worker actors. These worker actors can be spread across the cluster, ensuring that the workload is efficiently balanced and processed in parallel. Singletons. Sometimes, you need to ensure that only one instance of a particular actor exists and runs across the entire cluster. Actor frameworks provide cluster singleton patterns that guarantee this, even if the node hosting the singleton fails, in which case it's automatically moved to another healthy node. This is useful for managers or coordinators of global resources. Example scenarios. The power of distributed actors enables the creation of truly massive and resilient applications. Massively multiplayer online games, MMOs. Each player, monster, or critical game object can be an actor. When a player logs in, their actor is activated on a suitable game server in the cluster. As they move to different areas, their actor and associated state might seamlessly migrate to other servers to balance load. IoT backend. Thousands or millions of sensors, each represented by an actor maintaining its unique state and processing incoming data. As new sensors come online, new actors are instantiated and distributed across the cluster. Financial trading systems. Individual asset classes or trading pairs can be managed by specific actors. Orders, trades, and market data flow as messages to these actors, which process them in a highly concurrent and fault-tolerant manner across a grid of servers, ensuring low-latency execution and high throughput. The actor model's ability to seamlessly transition from managing concurrent operations on a single machine to orchestrating complex distributed interactions across vast networks is a testament to its visionary design. By providing location transparency, robust clustering, and sophisticated state management techniques, It offers developers a powerful and elegant paradigm for building the next generation of scalable and resilient internet-scale applications. Chapter 8, Advantages and Challenges, the Actor Model's Trade-offs. We've dedicated the preceding chapters to celebrating the Actor Model's elegance and power, from its fundamental principles to its real-world implementations and distributed capabilities. However, like any powerful tool, the Actor Model is not a silver bullet. Every architectural choice comes with trade-offs. In this chapter, we'll offer a balanced perspective, delving into the undeniable advantages while also candidly discussing the challenges and complexities that can arise when adopting the Actor Model, and ultimately, clarifying when it's truly the right choice. The unquestionable advantages. Let's recap and deepen our understanding of the significant benefits the Actor Model brings to the table. Native scalability. The Actor Model is inherently designed for scalability. Its core tenets, isolation and asynchronous message passing, mean that actors are naturally suited for horizontal scaling. Because there's no shared mutable state, actors can easily be distributed across multiple CPU cores on a single machine or spread across hundreds of machines in a cluster. Adding more capacity often means simply adding more actors or more machines, making it ideal for systems that need to handle fluctuating and massive loads. Inherent fault tolerance. This is arguably the Actor Model's most celebrated advantage. The let it crash philosophy, coupled with supervision hierarchies, fundamentally changes how resilient systems are built. Instead of agonizing over every potential error leading to a crash, developers can design for recovery. If an actor fails, its supervisor restarts it in a clean state, ensuring that failures remain localized and the system as a whole remains operational and available. This leads to truly self-healing applications with remarkable uptime. Simplicity of concurrency logic. For individual actors, concurrency problems virtually disappear. By processing messages sequentially, an actor eliminates internal race conditions, deadlocks, and the need for complex locking mechanisms. Reasoning about an actor's behavior becomes much simpler. It reads a message, processes it, and updates its own state. This significantly reduces the cognitive load on developers, allowing them to focus on business logic rather than low-level synchronization primitives. High responsiveness. The asynchronous, non-blocking nature of message passing ensures that actor systems remain highly responsive. An actor sends a message and immediately continues its work, never waiting for a response unless explicitly designed to do so, e.g., using ask patterns with futures. This prevents bottlenecks and ensures the system can handle many concurrent operations without becoming sluggish, critical for user-facing applications and real-time processing. Isolation and modularity. Actors are independent, self-contained units of computation. This promotes highly modular design, where concerns are clearly separated. This isolation makes actors easier to develop, test, and even reason about in isolation, improving overall code quality and maintainability. Suitability for event-driven architectures. The actor model perfectly aligns with event-driven principles. Actors react to incoming messages, events, process them, and often emit new messages, events, as a side effect. This makes them ideal citizens in reactive systems, microservices, and other architectures built around message flows and asynchronous communication. The real-world challenges. Despite its powerful advantages, adopting the actor model comes with its own set of complexities and trade-offs that developers need to be aware of. Paradigm shift learning curve. Thinking differently. The biggest hurdle for many developers is the fundamental paradigm shift. Most are accustomed to object-oriented programming, OOP, or imperative styles, where direct method calls and shared memory are common. The actor model requires thinking in terms of independent, message-passing entities. This means abandoning familiar patterns like direct method calls in favor of sending messages, and learning to manage state without direct external access. Debugging mindset. Troubleshooting an actor-based system is different. Instead of stepping through a call stack, you often need to trace message flows across multiple actors, potentially on different machines. This requires a different set of debugging tools and techniques, often focusing on logging, tracing, and monitoring message interactions. Debugging distributed actor systems. Opacity. While individual actors are simple, a large, distributed actor system can be opaque. Messages can be in transit, actors can be migrating, and failures can occur in unexpected places. Recreating specific faulty scenarios can be extremely difficult due to the non-deterministic nature of distributed execution. Tooling. Traditional debuggers are less effective. Effective debugging necessitates robust logging, distributed tracing, e.g., using correlation IDS in messages, metrics collection, and live monitoring of actor behavior and message throughput, ensuring message order and delivery guarantees. Message order. While messages sent to a single actor are guaranteed to be processed in order, there is no global guarantee of message order between different actors in a distributed system. If actor A sends message X to actor B and message Y to actor C, there's no guarantee that B will process X before C processes Y, or even that both messages will arrive. Delivery guarantees. As discussed, most systems offer at most once delivery by default, meaning messages can be lost. Achieving stronger guarantees, at least once, or exactly once, requires additional mechanisms like acknowledgements, retries with unique identifiers, or persistent message queues, which add complexity. Backpressure and resource management. Overwhelm. Because message sending is asynchronous, it's possible for a fast-producing actor to overwhelm a slow-consuming actor, leading to the consumer's mailbox growing unboundedly and eventually consuming all available memory. Strategies. This requires careful design using mechanisms for backpressure, slowing down the sender when the receiver is overloaded, or implementing bounded mailboxes, which proactively reject messages if the queue is full. State management across restarts. Ephemeral nature. By default, an actor's state is in memory and lost on restart. For critical state, developers must explicitly implement persistence mechanisms, saving to a database or using event sourcing. This adds design and implementation overhead. Clean slate versus continuity. Deciding when an actor should restart with a clean slate versus recovering its last known good state is a crucial design decision, often tied to its role in the system. When to choose the actor model, and when not to. Given these trade-offs, how do you decide if the actor model is the right fit for your project? Good fit when high concurrency parallelism is required. You have many independent tasks that need to run simultaneously. Fault tolerance is critical. The application must be highly available and resilient to failures, e.g., telecom, financial systems, large-scale web services, IoT. Distribution is inevitable. The system naturally scales out across multiple machines. Event-driven nature. The problem domain naturally maps to events and reactions, e.g., streaming data processing, real-time gaming, complex event processing. Many independent stateful entities. The system manages a large number of distinct, logical entities that can operate largely independently, e.g., user sessions, trading accounts, IoT devices. Not a good fit or overkill when simple CRUD applications. For basic create, read, update, delete operations on a database, traditional web frameworks are often simpler and more efficient. Batch processing. For applications that primarily perform large, sequential, CPU-bound computations, e.g., numerical analysis, offline data processing, where data parallelism might be a better fit. Strict synchronous request response. If the entire system is built around strictly synchronous request-response interactions and doesn't require high concurrency or resilience levels from its core. Small, monolithic applications. The overhead of managing an actor system runtime might outweigh the benefits for small-scale applications that don't face concurrency or scalability challenges. Hybrid approaches. It's important to note that the actor model doesn't demand an all-or-nothing commitment. Many successful large-scale systems are polyglot, using actor frameworks for their highly concurrent, fault-tolerant core, while integrating with other technologies, e.g., traditional databases, REST APIs, message queues, for different aspects of the system. Ultimately, the actor model provides a powerful mental model and robust tools for tackling some of the hardest problems in modern software development. Understanding its nuances, both strengths and weaknesses, empowers architects and developers to make informed decisions and build truly resilient and scalable systems for the future. Chapter 9, Actor Thinking Beyond the Code. By now, you understand the components of an actor, the mechanics of message passing, and the robust fault tolerance mechanisms that define the actor model. We've explored the real-world frameworks that implement these ideas and weighed their advantages and challenges. But knowing the technical details is only part of the journey. To truly harness the power of the actor model, you need to cultivate actor thinking, a shift in mindset that influences how you design systems, solve problems, and structure your applications. This isn't just about syntax or specific API calls. It's about a different way of conceptualizing concurrent computation. Cultivating an actor mindset. The transition from familiar programming paradigms to actor thinking often requires letting go of deeply ingrained habits. From shared state to message passing, the most fundamental shift is moving away from the idea that components directly interact by inspecting or modifying shared memory. Instead, all interaction occurs via asynchronous messages. This means designing data flows rather than control flows. From direct calls to indirect communication, no longer do you call a method on an object. Instead, you send a message to an actor. The sending actor doesn't know or care how the receiving actor processes the message. It trusts the recipient to handle it. From predicting failure to expecting recovery, embrace the let it crash philosophy. Instead of building overly complex logic to prevent every possible error at every point, design for quick detection and clean recovery orchestrated by supervisors. Identifying actors in your problem domain. The first step in applying actor thinking is to identify potential actors within your system. This often involves looking for active entities. What are the independent, autonomous components in your problem domain? What entities have their own state and responsibilities? Analogy. In an organization, who are the independent people or departments? Each person or department has their own responsibilities, their own state, their current tasks, knowledge, and they communicate by sending messages, emails, memos, verbal requests. Encapsulated state. What pieces of state need to be managed and mutated, but only by a single, responsible entity? Message-driven interactions. What are the natural communication points? What information needs to flow between these entities? What commands, queries, or events drive the system? Examples. User session. A user session actor manages the state for a single logged-in user. It processes login, logout, receive message, send messages, maintaining the user's online status and presence. Order processor. An order actor handles the lifecycle of a single customer order. It receives place order, add or remove item, process payment, ship order messages, and maintains the order's current status, e.g., pending, paid, shipped. Device controller. An IoT device actor represents a single smart device. It receives command messages, e.g., turn on light, sends telemetry messages, e.g., temperature reading, and maintains the device's operational state. Game character. In a game, each player's character, or even a non-player character, NPC, might be an actor. They receive move, attack, interact messages, and maintain their position, health, and inventory. Designing messages and protocols. Once you've identified your actors, the next step is to meticulously design the messages they will exchange. Messages as contracts. Treat messages as explicit contracts between actors. A message should have a clear purpose and contain all the necessary, immutable data for the recipient to perform its task. Clear intent. Instead of generic data structures, name your messages to convey intent. Add quantity, product ID. Quantity is clearer than update data. Immutability. Reiterate the importance of immutable messages. This prevents unintended side effects and ensures that once a message is sent, its content is fixed. Beyond individual messages, think in terms of interaction protocols, sequences of messages that constitute a complete transaction or workflow. Example, authentication protocol. User sends login request, username, password hash to auth actor. Auth actor sends verify credentials, username, password hash to database actor. Database actor sends credentials verified, user ID, or credentials invalid to auth actor. Auth actor sends login success, session ID, or login failure to the original requester. Structuring actor hierarchies. Designing effective supervision hierarchies is crucial for building robust systems. Logical breakdown. Think about how to group actors so that a parent actor effectively manages the life cycle and failures of its children. Children often relate to a subcomponent, a specific request, or a unit of work. Delegation of responsibility. The parent delegates complex tasks to its children. If a child fails, the parent, as the supervisor, makes the recovery decision. Fault isolation. Structure your hierarchy to isolate faults. A failure in one branch of the tree should not necessarily bring down the entire system. For example, all actors handling WebSocket connections might be children of a connection manager actor. So if one connection actor crashes, only that connection is affected, not all connections. Managing state the actor way. Actor thinking requires a disciplined approach to state management. Internal, sequential updates. All state changes occur strictly within the actor itself as it processes messages sequentially. This is central to avoiding concurrency issues. Immutable data structures for state. While an actor's internal state is mutable by the actor, using immutable data structures, where a modification returns a new version of the data rather than changing the old one, within an actor can further simplify logic and prevent subtle bugs. Coarse-grained versus fine-grained. Decide at what granularity your actors should exist. A customer actor for every customer could lead to millions of actors. Perhaps an account manager actor handles all accounts for a region, or a transaction actor is created only for the duration of a specific monetary transaction. The choice depends on the system's needs for isolation, fault tolerance, and concurrency. Thinking about failure and recovery first. One of the most liberating aspects of actor thinking is the inversion of the error handling paradigm. Instead of obsessing over prevention, you design for resilient recovery. Embrace transients. Assume individual actors are transient. They can crash, restart, or be moved. The state that matters needs to be persisted externally if it must survive. Design supervision strategies. For each type of actor, explicitly consider: if this actor fails, what is the appropriate strategy for its supervisor? Resume, restart, stop, escalate. Circuit breakers and timeouts. Proactively design patterns to handle external service failures and unresponsive actors without bringing down your own system. Analogies and mental models for actor-oriented design. To foster actor thinking, it helps to use relatable mental models. The organization chart. Imagine a company hierarchy. Each person actor has a job description, behavior, and a desk state. They receive instructions, messages from their manager, supervisor, or colleagues. If someone gets sick, fails, their manager handles it, perhaps replacing them, restart, instructing them to rest, resume, or firing them, stop. Biological cells. Cells actors operate independently in a body. They have their own DNA, behavior, and organelles, state. They communicate by chemical signals, messages. If a cell malfunctions, the body has mechanisms to destroy and replace it. The ant colony. Each ant actor follows simple rules and communicates via pheromone trails, messages. Collectively, they exhibit complex, robust behavior like building nests and finding food, even if many individual ants fail. Reframing common design patterns in actor terms. Many traditional design patterns can be reimagined and simplified using actors. State machine. An actor changing its behavior, using become, naturally implements a state machine where each behavior represents a state. Producer-consumer. A producer actor sends messages, items, to a consumer actor's mailbox queue. The actor model handles the thread pooling and synchronization. Load balancing/routing. A central router actor can receive messages and forward them to a pool of worker actors, distributing the workload. Visitor pattern. Messages encapsulating operations, visit actors, which apply local logic. Cultivating actor thinking is an ongoing process. It's about shifting your intuition from a world of shared resources and direct calls to one of isolated, communicating entities. This mindset, once adopted, can profoundly simplify the design and development of highly concurrent, scalable, and resilient systems, clearing away the concurrency conundrum that once seemed insurmountable. Chapter 10. The future is reactive, actors in a connected world. Throughout this book, we've journeyed from the historical crucible of concurrency challenges to the elegant simplicity of the actor model, dissecting its inner workings, surveying its real-world implementations, and cultivating the unique mindset it demands. We've seen how actors, with their isolated state and message-driven interactions, offer a powerful antidote to the complexities of shared memory concurrency, paving the way for inherently scalable, fault-tolerant systems. Now, as we look to the horizon, it becomes clear that the actor model is not just a solution for past and present problems, but a foundational paradigm for the future of software development. It aligns perfectly with the demands of an increasingly interconnected, real-time, and resilient digital world. The Reactive Manifesto and its principles. The actor model finds a powerful contemporary expression in the principles of the Reactive Manifesto. Published in 2014, this document outlined a set of core characteristics for systems that are designed to meet the demands of modern applications. Systems that are robust, responsive, and scalable. The manifesto identifies 4 key traits. Responsive. Systems must respond in a timely manner. Responsiveness is the cornerstone of usability and utility. Actors, with their asynchronous, non-blocking message passing and single-threaded processing of individual mailboxes, are inherently designed to remain quick and unblocked, ensuring consistent response times. Resilient. Systems must stay responsive in the face of failure. As we've extensively discussed, the actor models, let it crash, philosophy, and powerful supervision hierarchies are the ultimate embodiment of resilience. Failures are contained, components are automatically recovered, and the system gracefully endures disruptions rather than collapsing. Elastic. Systems must remain responsive under varying load. They should be able to scale up or down as needed. The inherent location transparency and easy distribution of actors make them exceptionally elastic. You can add more actor instances or deploy them across more machines, and the underlying framework will distribute the workload, allowing the system to handle increasing demands seamlessly. Message-driven. Reactive systems rely on asynchronous message passing to establish a loose coupling between components. This is the very essence of the actor model. Actors communicate exclusively through messages, promoting encapsulation, isolation, and ultimately, ensuring that components are isolated from each other's failures and can evolve independently. The actor model isn't merely compatible with the Reactive Manifesto. It is, in many ways, its ideal implementation, providing a concrete and proven blueprint for building truly reactive systems. Actors and event-driven architectures, EDA. The world is increasingly becoming event-driven. From user interactions and sensor readings to financial transactions and IoT telemetry, systems are driven by streams of discrete events. Event-driven architectures, EDA, are designed to process, react to, and emit these events. The natural synergy between actors and EDAs is undeniable. Actors are fundamentally event handlers and event emitters. They receive messages, which can be considered events, process them based on their internal state and behavior, and then often emit new messages, new events, as a result. This makes actors ideal components in an EDA. Consumers of events. An actor can subscribe to an event stream from a message broker like Kafka or RabbitMQ and process each event as an incoming message, updating its state or initiating further actions. Producers of events. After performing its work, an actor can emit new events to an event stream, notifying other actors or external systems about changes or occurrences. This tight alignment allows actor systems to seamlessly integrate with broader enterprise architectures that leverage event streams for data consistency, auditing, and inter-service communication. Actors and microservices. The microservices architectural style has gained immense popularity for building large, complex applications as collections of small, independent, loosely coupled services. Each microservice typically focuses on a single business capability and communicates with other services over a network. How do actors fit into this picture? Microservices as coarse-grained actors. You can think of individual microservices as large, coarse-grained actors. They communicate via messages, often HTTP requests or message queues, and maintain their own encapsulated state. They are designed for independent deployment and scaling. Actors as microservice internals. The actor model provides a superb framework for implementing the internal logic of a single microservice. Instead of using traditional threads and locks within a microservice, you can use an actor system, like Akka or Orleans, to manage its internal concurrency, state, and fault tolerance. This allows a microservice to handle many concurrent requests efficiently, manage complex state without shared memory issues, and recover from internal failures, all benefiting from the actor principles. This complementary relationship means that the actor model can provide the fine-grained concurrency and resilience within each microservice, while the microservices architecture provides the higher-level separation and deployment independence across services. Actors in cloud-native computing. The rise of cloud computing, with its promises of elasticity, global distribution, and pay-as-you-go economics, perfectly amplifies the strengths of the actor model. Cloud-native applications are designed from the ground up to leverage the benefits of cloud platforms. Virtual actors in the cloud. Frameworks like Microsoft Orleans, with its concept of virtual actors, directly cater to cloud-native development. They abstract away the complexities of distributed state, actor activation, and routing across potentially ephemeral and dynamic cloud infrastructure. Developers can write actor logic, and the cloud runtime transparently scales and manages thousands or millions of actor instances. Containerization, Docker, and Kubernetes. Actor systems often run beautifully on container orchestration platforms like Kubernetes. Each actor application component can be packaged into a Docker container. Kubernetes can then dynamically scale the number of these containers based on load, automatically distributing actor instances across the available server fleet and restarting them if they fail, echoing the resilience of actor supervision. But at the infrastructure level, serverless/function-as-a-service, FaaS. While not directly the actor model, FaaS platforms like AWS Lambda or Azure Functions share a philosophical underpinning. Small, independent units of computation that are invoked by events maintain no persistent state between invocations and scale on demand. You can design serverless functions to behave in an actor-like manner, communicating via external message queues, bringing some of the benefits of isolation and message-driven behavior. Emerging trends and speculations. The adaptability of the actor model suggests its continued relevance in future technological landscapes. IoT and edge computing. As billions of devices become interconnected, managing their unique states and communication will be a monumental task. Actors, with their ability to model independent, stateful entities that communicate via messages, are incredibly well suited for orchestrating IoT devices at the network's edge, where connectivity can be intermittent and failures common. Blockchain and decentralized ledger technologies. In the world of decentralized computation, actors could model individual participants, smart contracts, or transaction validators, processing information and making decisions autonomously while contributing to a global, distributed ledger. AI and machine learning. Actors can represent intelligent agents in simulations, distributed machine learning model trainers, or even components of real-time AI systems that need to process vast amounts of data concurrently and reactively. Swarm intelligence, where many simple agents cooperate to perform a complex task, has a very actor-like flavor. Concluding thoughts. The journey through the actor model reveals a powerful truth. Simplicity, especially in the face of complexity, is often achieved through elegant abstraction. By embracing isolation and message passing as fundamental tenets, the actor model offers a principled way to manage the inherent challenges of concurrent and distributed computing. It reframes the very essence of how we build software, moving us from a world of shared, often fragile, resources to one of resilient, autonomous, and communicating entities. This book has aimed to equip you with a foundational understanding of this paradigm, to inspire actor thinking, and to showcase its profound impact on modern systems. The actor model is not merely a niche technology. It is a timeless conceptual framework whose principles are more relevant than ever in our hyperconnected, real-time world. By adopting its mindset and tools, you can build systems that don't just work, but work reliably, scale effortlessly, and truly unleash the full potential of concurrent and distributed computation. The future is reactive, and actors are poised to play a central role in building it. Further reading and resources. To continue your exploration of the actor model, consider diving into these resources. Seminal papers. Carl Hewitt's original papers on the actor model, e.g., a universal modular actor formalism for artificial intelligence. Gul Agha's Actors, a model of concurrent computation in distributed systems. Key books: Programming Erlang, Software for Concurrent Applications by Joe Armstrong, Akka in Action from Manning Publications, books on the Reactive Manifesto, Framework Documentation. The official documentation for Erlang/OTP, Akka, and Microsoft Orleans are comprehensive and provide practical guidance. Online communities and forums. Conferences, user groups, and online forums dedicated to Erlang, Akka, Orleans, and functional programming are excellent places to learn from experienced practitioners and stay updated on new developments. Reactive Manifesto website, reactivemanifesto.org for the foundational principles.